You see a photograph. Your brain instantly recognizes a face, a tree, a car. But how does a computer do the same? It's not magic. It's a carefully crafted process, a digital eye built layer by layer. This process, refined over years, allows machines to interpret the visual world around us, transforming raw pixels into meaningful understanding. It's a fundamental building block for everything from self-driving cars navigating complex city streets to sophisticated medical image analysis identifying subtle anomalies. This is the dawn of computational sight, a revolution in how machines perceive reality. At the heart of this digital sight lies the Convolutional Neural Network, or CNN. Think of it as a specialized brain designed solely for understanding images. It doesn't see the whole picture at once, like a human might, but rather dissects it into manageable parts, much like an artist meticulously studies a subject's contours and textures before committing brush to canvas. This methodical, segmented approach is what gives CNNs their remarkable power and accuracy in complex image recognition tasks, allowing them to process visual information with unparalleled detail. The journey begins with convolution, the core operation. Imagine a tiny magnifying glass, a filter, sliding across the entire image, pixel by pixel. This filter is not random. It's programmed to look for something very specific: a simple edge, a sharp corner, a subtle curve, or a particular color gradient. It's a digital probe, meticulously scanning each section of the image for the most basic visual elements, acting as the first, crucial step in a complex analytical chain designed to break down complexity. As this specialized filter moves across the image, it highlights areas that precisely match its programmed pattern. If the filter is designed to detect vertical lines, it will activate strongly where those lines appear in the image data. This process creates a feature map, a new, transformed representation of the original image, emphasizing the presence and precise location of those specific, low-level features. It's like creating a stencil of all the straight edges in a picture. But one filter, looking for just one specific pattern, isn't enough to understand a complex scene. A CNN employs a multitude of different filters simultaneously, each trained to identify a unique elementary feature. Some look for horizontal lines, others for diagonals, gentle curves, sharp angles, or even subtle variations in color intensity. Each unique filter generates its own distinct feature map, contributing a unique perspective on the image's composition and effectively building a rich tapestry of basic visual information. This entire process of applying multiple filters forms the foundational layer of the CNN's understanding. It's akin to teaching a very young child to distinguish between fundamental shapes and lines. These feature maps are the raw ingredients, the most primitive visual elements extracted from the raw pixel data, representing the initial breakdown of reality into its most basic building blocks. They are the essential cues upon which all subsequent, more complex understanding will be built. Following convolution, the network employs a technique called pooling. This step is designed to simplify the feature maps, effectively reducing their size and the amount of data the network needs to process. Think of it as summarizing a lengthy document by extracting only the most crucial sentences. Pooling retains the most significant information, like the strong presence of an edge, while discarding redundant or less important details. This compression makes the network more computationally efficient and significantly helps to prevent overfitting, where a model becomes too specialized to its training data. This pooling operation makes the entire network more robust and generalized. It means the network can still reliably recognize an important feature, like a vertical edge, even if that edge is slightly shifted in position within the image or appears at a subtly different angle. It's learning to see the broader patterns and the essence of an object, rather than becoming fixated on precise pixel locations. This invariance to small spatial translations is absolutely crucial for real-world image recognition, where objects can appear in countless positions and orientations. Then, the CNN repeats the process, but at a higher level of abstraction. The simplified feature maps from the pooling layer are fed into a new set of convolutional layers. These subsequent layers utilize more sophisticated filters, designed not just to find basic edges, but to detect combinations of those basic features. This is where the network begins to assemble simple visual components into more meaningful, complex patterns and structures, moving beyond mere lines and curves. These deeper convolutional layers are where the real pattern recognition takes shape. They might learn to detect simple geometric shapes like circles or squares by recognizing specific arrangements of edges and curves. Following layers can then identify more complex visual elements. A wheel by combining circular shapes and linear components, or a human eye by recognizing specific arrangements of curves and textures. Each layer builds upon the abstractions identified by the previous one, creating a sophisticated hierarchy of visual concepts. It's a deeply hierarchical process, mirroring how biological vision systems are thought to work. Lower layers of the network are responsible for detecting simple elements like points and lines. As the data progresses upwards through the network, subsequent layers combine those simple elements to recognize increasingly complex structures, textures, then parts of objects like ears or legs, and finally, the complete objects themselves. This multi-layered abstraction, building from simple to complex, is the core engine of deep learning for computer vision. Imagine constructing something with Lego bricks. The very first layers of the CNN are like recognizing individual bricks based on their shape and color. The next layers are like seeing how those bricks can be assembled to form a simple wall or a base. Finally, the top layers are capable of recognizing an entire, complex structure like a miniature house, built from those fundamental components. This analogy clearly highlights how complex objects are ultimately constructed from simpler components, identified and combined step by step within a CNN. After multiple cycles of convolution and pooling, the network has progressively built a rich, hierarchical representation of the image's visual components, from the most basic to the more complex. But how does it translate this complex internal understanding into a definitive output, like confidently saying, "This image contains a cat"? This is where the final stages, the fully connected layers, come into play. These layers take the highly abstract, high-level features that have been meticulously extracted by the preceding convolutional and pooling layers and flatten them into a single, long list of numerical values. Think of this as gathering all the identified and understood visual parts of the image and presenting them as a concise summary. These flattened features represent the network's distilled, comprehensive understanding of the image's content. These connected layers then function as a sophisticated classifier. They analyze and weigh the evidence presented by all the detected features from the earlier layers, the specific combination of whisker patterns, the presence of triangular, pointy ears, a characteristic furry texture, and a certain characteristic body shape. Based on this collective evidence, the network makes a final prediction about what the image depicts. It's the critical decision-making stage, synthesizing all the learned visual cues into a confident output classification. During training, the network is shown millions of labeled images. It learns to adjust the filters and the weights in its fully connected layers to minimize errors. If it incorrectly identifies a dog as a cat, it receives a signal to adjust its internal parameters. This iterative process, like a student repeatedly practicing problems, refines the network's ability to make accurate predictions over time. This training process is what imbues the CNN with its intelligence. It's not programmed with explicit rules like, if it has whiskers, it's a cat. Instead, it learns these associations implicitly from the vast amount of data it processes. The network discovers the complex statistical relationships between pixel patterns and object labels on its own, a testament to the power of data-driven learning. Consider the sheer scale. A single CNN might have millions, even billions, of parameters, the values that define the filters and the connections between layers. Each of these parameters is fine-tuned during training. This immense complexity allows CNNs to capture incredibly subtle nuances in images that would be imperceptible to human observers. This architecture is incredibly versatile. While we focused on recognizing cats, the same fundamental principles apply to countless other vision tasks. Identifying cancerous cells in medical scans, recognizing different car models for autonomous driving, detecting defects in manufacturing lines, or even analyzing satellite imagery for environmental monitoring. The ability to see and interpret visual data is a cornerstone of modern AI. However, like any powerful tool, CNNs have limitations. They are exceptionally good at recognizing patterns they were trained on, but they can be surprisingly brittle when faced with novel or adversarial examples. A slight change in lighting, an unusual angle, or even strategically placed visual noise can sometimes fool a network completely. This vulnerability highlights a crucial point. The AI doesn't truly understand an image in the human sense. It's a master of pattern matching, incredibly effective at its task, but lacking genuine consciousness or contextual reasoning. It identifies features and makes probabilistic associations based on its training data, a powerful statistical engine rather than a sentient observer. The performance of a CNN is entirely dependent on the quality and quantity of its training data. Biased or incomplete datasets can lead to biased or inaccurate models. If a network is only trained on images of white cats, it might struggle to recognize a black cat. Ensuring fairness and robustness requires careful consideration of the data used to build these visual systems. So, while the ability of AI to see has advanced dramatically thanks to architectures like CNNs, it's built on a foundation of specific mathematical operations and massive data processing, not innate comprehension. It's a sophisticated imitation of perception, a triumph of engineering and computational power that continues to evolve. This system, painstakingly built from filters and layers, learns to identify a cat by statistically correlating pixel patterns with the label cat across millions of examples. It's a powerful engine for visual recognition, but it's the intricate design choices and the sheer volume of data that enable its impressive feats, not some emergent understanding of feline characteristics. If this journey into how AI learns to see clicked for you, a like and a subscribe are the whole payment for the hours spent dissecting those filter behaviors. They are why there will be another explanation next week.